now going to look at a required practical, and it's to investigate how pH changes when a weak acid reacts with a strong base and when a strong acid reacts with a weak base. So the example we're going to look at is with ethanoic acid and sodium hydroxide. Ethanoic acid is the weak acid and sodium hydroxide is a strong base. So our method is split into two steps. The first part is calibrating the pH meter, and part two is the actual measuring of the pH of the mixture of acid and alkali. So for part one, first thing you do is rinse the pH probe thoroughly with deionized water and shake gently to remove the excess water. And we then place it into a standard pH 7 buffer solution. And then we record the pH because the pH meter will be close to 7, but it might be slightly off. So we need to record that pH that it's measured. And then we repeat for pH 4 and 9.20 buffer solutions. So we have a recorded value of the pH for an acid and an alkali. And then we plot a graph of the pH of the buffer solution over the recorded pH reading. And this is so that we can obtain something called a calibration curve, where it'll help us in part two when we've recorded the pHs, and then we need to use this calibration curve to find out actually what the pH is when we shift it along slightly because of the inaccuracy of the probe. And so for part two, the first thing we do is rinse a burette with 0.1 moles per deciliters cubed of ethanoic acid, and we make sure to fill this all the way to the bottom below the tap and that there are no bubbles. And then we transfer 20 centimeters cubed of this acid to a clean beaker, which is 100 centimeters cubed. And then we rinse a second burette with the same 0.1 mole per deciliters cubed, but of sodium hydroxide this time. And again, we fill it up right to the bottom without any bubbles. And then we rinse the pH probe with distilled water and clamp it so that the bulb is fully immersed in the beaker, and use a rod to stir the solution gently and record the pH of the acid. And then we add 2 centimeters cubed of sodium hydroxide to the beaker using the burette, and we stir the mixture gently and record the pH. And we repeat this until we have added 18 centimeters cubed of sodium hydroxide. And then after that, we take pH readings every 0.2 centimeters cubed of sodium hydroxide that has been added until 22 centimeters cubed has been reached. And then we take the readings every 2 centimeters cubed added again until 40 centimeters cubed has been added. So the diagram on the right is of a normal titration, but the setup would be like this, but with a pH probe and using a beaker instead of a conical flask. So in the burette at the top, we would have the sodium hydroxide, and in the beaker at the bottom, we would have the ethanoic acid and the pH probe, and probably a stirring rod. So then after we've done the experiment, what we should get is we should firstly have the calibration curve. So that will be on the Y, we would have the pH of the buffer solution, and on the x-axis we should have the recorded pH by the pH probe. And so we had 7, which I'll put here, and then 9.20, and then 4. So at 4, the recorded pH might not be 4 exactly. It could be, let's say, 4.2. So then we would mark on the value of it. So we would plot that. And then for 7, maybe it was 6.9. So then we would plot that. And then for 9.2, maybe it was 9.24. And so we plot that. And then we draw a straight line through these and that will be our calibration curve. So then when we actually use the pHs that we recorded in the part 2, we can adjust the pH according to the inaccuracy of the probe. And then what we do is we plot a graph, another one of, on the y this time it will be the adjusted pH. So after using the calibration curve, what the pH value is, and then we have the volume of sodium hydroxide added. And your curve should look something like this. So it should start off as an acid, so maybe around 3, and then it should be a slow rise, and then we have a straight line here, and then it levels off at the top. So at the end of it, there's no dramatic increase in pH because we call this the end point, and there's a surplus of H+ ions. And we call this point here, where there is a dramatic increase in pH, the equivalence point. Or the end point. Now we're going to look at some questions. So for the first question, these titration curves are for combinations of different aqueous solutions of acids and bases, and all the solutions have concentration of 0.1 moles per deciliters cubed. Identify which graph is the following. So for A, they want the addition of 25 centimeters cubed of ammonia to. So ammonia is a weak base, and hydrochloric acid is a strong acid. And it's very useful to remember some of these weak bases, strong acids, strong bases, weak acids examples, because sometimes they will ask you about different chemicals without telling you whether they are weak bases and strong acids. So usually weak acids are the ones which are carboxylic acids, so organic molecules, and the strong acids will be the hydrochloric acid or sulfuric acid, nitric acid, those kinds of acids. The strong bases will be the hydroxides, so you have sodium hydroxide, potassium hydroxide, and you need to remember that ammonia is a weak base. And so what we expect with this graph is that it should start off at quite a low pH because we start off with the HCl before the NH3 is added. So we should have a very low pH to start off with. So right away we can rule out D, and then we can rule out A as well. So it's between B and C. So now we look at NH3. So NH3 is a weak base, and that means that the ending of the curve should be not very high, because the pH of a weak base will be closer to 7 compared to 14, and so it must be C. And then for B, the addition of 25 centimeters cubed of sodium hydroxide to ethanoic acid. So sodium hydroxide is a strong base, and the ethanoic acid, like all organic molecules, is a weak acid, sorry. And so we start off with quite a high pH, and then end with a really, really high pH. And so it must be A. And then for C, we have nitric acid, which is a strong acid. And then potassium hydroxide, which is a strong base. So we have a strong acid being added to a strong base. And so it must be D, because this is the only curve where we start off with the base and we're adding an acid to a base. And so the answer is D.